Okay, so let's dive into the world of matrices. And I know what you might be thinking, but we're going to go way beyond the dry textbook stuff here. Because it turns out matrices aren't just these boring boxes of numbers. Nope, they're actually powerful little machines that can transform images and solve some really complex problems, all based on a few surprisingly simple rules. For so many of us, when we see this, it's just, well, a box of numbers, right? It might even be a little intimidating, something you vaguely remember from a math class you took years ago. It just sits there, a static object, a collection of figures inside some brackets. But believe me, that is not the whole story. A much, much better question, and the one we're really going to dig into, is what can a matrix actually do? Because a matrix isn't just a thing, it's an action. It's a machine waiting for a job. And you know, every machine needs something to work on. So for our little experiment today, we've got this picture of some Saluki dogs. We're going to take the coordinates of every single point in this image, feed them into our different matrix machines, and see what pops out on the other side. So first up, let's look at what might be the most visual and, honestly, the most intuitive power of matrices, their ability to literally transform pictures right before our eyes. Okay, so here's the key idea you need to grab onto. A matrix is just a set of instructions. That's it. Each number inside this box is part of a rule that takes the original coordinates of a point, we can call them x, y, and tells them exactly where to move to create a brand new point. We've got to start with the most basic one of all, the identity matrix. The easiest way to think about it is like the number 1 in multiplication. When you apply it to our picture, well, absolutely nothing happens. It's our starting point, our baseline, our do-nothing command. Okay, time to get our hands dirty. Here's our first real experiment. Look at this new matrix. We've only made one tiny little change. That 1 in the top left corner is now a -1. So, how could one little sign change possibly affect the entire picture? Any guesses? And there you have it, a perfect mirror image. How cool is that? That one tiny change was a command. It told every single point in that picture to follow a new rule. You're going to become -x, y. So by just flipping the sign of every x coordinate, boom, it reflects the entire image across that vertical y-axis. All right, let's keep going. Our next matrix, as you can see, now has 2 -1s. The rule is -1, 0, 0, -1. So if one -1 gave us a reflection, what do you think's going to happen now that we have 2? It causes a full 180-degree rotation. This is a fantastic illustration of how this matrix sends every point, x, y, to its complete opposite, -x, -y. It's like every point on the dog just traveled in a straight line right through the center of the graph and came out the other side. Okay, for our last visual test, check this one out. It's a bit different. The numbers aren't just 1s and -1s anymore. We've got a 2 and a -1. This means our little matrix machine has 2 completely different jobs to do, and it's going to do them at the exact same time. And look at that. The 2 in the matrix told every x coordinate to double in value, which stretches the image horizontally. At the same time, that -1 told every y coordinate to flip its sign, reflecting the whole thing across the horizontal x-axis. 2 different actions packed neatly into one simple rule. So, we've seen how matrices are these incredible rules for transforming shapes. But that's really just one of their superpowers. They can also act as powerful organizers, bringing a kind of beautiful order to the often messy world of algebra. Take a look at this. On top, you've got a pretty standard system of 2 linear equations. It looks a little cluttered, right? But watch this. By just plucking out the important numbers, the coefficients, the variables, and the answers, we can rewrite the whole thing as one single, clean matrix equation. A times x equals b. And this isn't just about making it look neater. It makes it incredibly powerful to solve. Okay, so having the equation organized is a great first step. But how does that actually help us find the answer? I mean, how do we get that x all by itself? Well, to do that, we need to somehow undo the action of matrix A. We need a special tool for the job. You know how division undoes multiplication? We need something just like that for our matrix A. And in the world of matrices, that tool is called the inverse matrix. You'll see it written as A with a little -1 exponent. And the process for using this undo tool it's just beautiful in its simplicity. We start with our organized problem, AX equals B. To get x alone, we just apply our undo tool, that A inverse to the left side. But you know how it goes with equations, you gotta keep things balanced. So we do the same thing to the right side. And now for the magic part. A inverse times A basically cancel each other out, leaving us with that do-nothing identity matrix from before. And just like that, the solution reveals itself. X is simply the inverse of A multiplied by B. And when you actually run the numbers for that problem we were looking at, this method cleanly spits out the answer. The solution to that whole messy system is just x equals 2 and y equals 5. No fuss, no complicated substitutions, just a clear, repeatable process. So we've seen matrices as picture transformers and as amazing equation solvers, but why is any of this so important? I mean, where does this stuff actually show up outside of a math class? This short answer is pretty much everywhere in modern technology. The transformations we just did on that Saluki picture, that's the fundamental math behind all computer graphics, from video games to Hollywood special effects. And the equation solving, that's absolutely critical for engineering, for data science, and even for artificial intelligence, where massive matrices are processing information in neural networks as we speak. And this really gets to the heart of why matrices are so revolutionary. They help us make this huge shift in our thinking. We move from just calculating individual answers, one by one, to seeing the entire structure of a problem all at once. We stop asking, what is the number? And we start asking, what is the underlying rule? Which kind of leaves us with a final big thought. We've just seen how these simple-looking boxes of numbers can describe reflections, rotations, and really complex systems. It really makes you wonder, what other hidden rules and structures are out there in the world, just waiting to be described and understood by a matrix?